So we talked about, for our light emitting diodes, we talked about how the photons are produced by the excess charge carriers. Now we want to know, okay, how many photons can we produce in the semiconductor, or how much light can we produce using that LED? So it's not a simple answer. So the amount of photons that are produced is going to depend on the semiconductor or the material. It's going to depend on the doping level of the semiconductor, and it's also going to depend on how much current you have in the semiconductor. So let's first look at the equations for the current components in a forward bias diode. So in my forward bias diode, or my forward bias PN junction, one of the current components is the minority electron diffusion current. And we'll write the current density. So that depends on doping concentration and some material properties like diffusion coefficient and diffusion length. As well as the bias voltage. Another component is the minority hole diffusion current. And then the last component is going to be the recombination current. And again, these are all current densities. And one important point is that this recombination current, this part of the current in the PN junction under forward bias, this recombination current does not contribute to the radiation or the production of photons. So this current component is non-radiative. It does, if we increase or decrease recombination current, it does not affect how many photons we are producing. Let's look at an example of this, and we'll consider the material gallium arsenide. Also remember, we want to be looking at direct bandgap semiconductors for LEDs, not indirect bandgap semiconductors. Gallium arsenide is a direct bandgap semiconductor, so we'll use it for this example. In gallium arsenide, the generation of photons is mostly due to electrons recombining. So let's figure out, when the electrons recombine, how many photons can be produced. So in order to do that, let's first define something called the injection efficiency. And for this example, the injection efficiency is going to be the electron diffusion current expressed as a ratio to the total current in the p-n junction. Okay, so injection efficiency will give a lowercase gamma as the symbol for that. And we're looking at electron diffusion current normalized to the total current density. So the total current density includes electron diffusion current, hole diffusion current, and our recombination current. Okay, so this is telling us, or for gallium arsenide, we know that the generation of photons is mostly due to the recombination of electrons. So we want to know in the current in our semiconductor, what fraction of that current is due to the movement of electrons, and that can give us an idea of how efficiently we can produce photons. But this is not the complete picture yet, because we're only looking at electrical currents right now. Not all of the electrons are going to recombine in such a way that they will produce a photon. So we can have a recombination of an electron occurring, or electron hole pair occurring, where it radiates a photon and where it does not radiate a photon. So let's define these two terms. I will have some recombination rate that results in the radiation of a photon, and that's going to be the excess electron concentration divided by the radiative lifetime. And then I'll also have some recombination rate. So this is the first equation. This is radiative recombination rate. And this next equation will be the non-radiative recombination rate. So non-radiative recombination rate, and that'll just be the excess electron concentration divided by the non-radiative lifetime. The total recombination rate is then going to be just the radiative recombination rate plus the non-radiative recombination rate. Now we can use these recombination rates to define something called the radiative efficiency. And this is going to be given a zeta as the symbol. So it's going to be the radiative recombination rate related to the total recombination rate in the denominator. Okay, now does this tell us the whole story of how much light the LED can produce? Well, not yet. We need to use the radiative efficiency and the injection efficiency to define something called the internal quantum. this internal quantum efficiency is going to be the amount of diode current that produces light. This is going to be expressed as a zeta sub I for internal, and that's going to be equal to the injection efficiency multiplied by the radiative efficiency. Okay, so now do we have a way to quantify how much light we're producing? And the answer is no, not yet. We're going to define another term, which is the external quantum efficiency. So this is the amount of light, or the amount of photons that actually, or the efficiency of the amount of light and photons that actually make it out of the LED. So this, if you're looking at an LED, this external quantum efficiency is going to tell you the efficiency of that LED at making photons that you can see. Or if there's a photodetector there, you know, the efficiency of the the production of photons that can be detected by that photodetector. So external quantum efficiency is going to be zeta sub ext. Now it's really complicated to relate this to internal quantum efficiency because this depends on a lot of factors. For example, the photon that's produced can be reabsorbed by the semiconductor material. Or, you know, the photon that's produced could be reflected by some interface before it makes it out of the LED. So we know that the external quantum efficiency is going to be less than the internal quantum efficiency, but there's no analytical form for this.